As you know that a spillway is a structure which is constructed at a dam site to dispose of the surplus flood or a surplus water from the upstream to downstream side. So now you know that the top of the crust is kept at the normal reservoir level. What is normal reservoir level? So normal reservoir level is that level where the water level rises up to that level under normal operating conditions. And during floods, the water level crosses the normal reservoir level and reaches up to the maximum reservoir level. So the difference between the maximum reservoir level and the normal reservoir level is known as the design head. So now when the reservoir gets filled up to the normal reservoir level, the water starts overflowing from over the top of the spillway crest, and the maximum level that it can reach is the maximum reservoir level. So depending upon the inflow rate, the water will start rising above the uh, reservoir level, and at the same time will overflow over the spillway crest. So water cannot rise above the maximum reservoir level. So therefore, if the spillway is provided, then it will dispose of the surplus water to the downstream side, as well as not allow the water to rise above the maximum reservoir level, because the spillways are designed for the head, for the design head. So the design head is the difference between the maximum reservoir level and the crest of the spillway. If these spillways were not provided, then during floods the water level would have reached normal reservoir level, and then would have exceeded the maximum reservoir level, and hence overtopped the dam and causing the failure of the dam. Hence, a spillway has to be provided to dispose of the surplus water at the dam site. So hence spillway is essentially also known as the safety valve for a dam. So it must be properly designed and must have adequate capacity to dispose of the entire surplus water during the floods. The shape of the lower nepi of a free-falling jet or a sharp-crested weir can be determined. So now generally, so you consider a case of a sharp-crested weir. So when the water level rises up to the crest, this is the crest of the sharp-crested weir. So when the water level comes to this level and then exceeds, then the jet of water first rises up, and then that is rises from the point O and reaches up to the crest, the point C, and then falls as a parabolic form. So now, if it was if a sharp crested weir, then the jet of water would be this. This is known as the lower nepi, this is known as the upper nepi, and this is the maximum reservoir level. The difference between the maximum reservoir and the crest is the head. So for an ogee weir, here the gap between the sharp crested weir and the lower nepi and the bottom is filled with concrete or a masonry, and hence attains a form, profile similar to an S shaped or an ogee shaped, and hence called the ogee weir or the ogee spillway. See, the lower nepi of a sharp crested that would come from a sharp crested weir would become the crest of the ogee spillway, but uh, the lower nepi of a free-falling jet will assume different profiles for different heads over the sharp-crested weir. So the profile of the ogee weir is generally confined to the lower nepi that would be obtained for the maximum head. Uh, uh, so we go on trying for various the profile for various heads, and but we fix up the profile of a lower nappy for the head which is maximum. So this is how we fix up the profile for the ogee weir. In the case of an overfall spillway or a sharp cluster, the water falls clearly away from the face of the spillway and the gap between the jet and the water is kept ventilated. While in Ogi spillway, the falling jet will adhere to the surface and there is no space between the weir as and the crest of the spillway under normal design conditions. The crest of the Ogi spillway can be made to conform to only a particular nappy that would be obtained for a particular head, and this head is known as the design head. So in practice, the actual head of water on the spillway called the operating head may be less or more than the design head. If the operating head on the spillway is more than the design head, then the lower nappy of the falling jet may leave the Ogi profile, thereby generating negative pressures. Due to the generation of the vacuum or negative pressures may lead to formation of the vapor bubbles when the absolute pressure reaches the vapor pressure. And these vapor bubbles are carried to the high pressure region where they burst and or collapse, resulting in a high impact on the surface. And this continuous impact removes small particles of a concrete or a masonry, causing formation of pits on the surface, which is known as pitting. And this particular phenomenon is known as cavitation. Hence, we can conclude that if the head of the water or the spillway is more than the design head, then the cavitation may occur. On the other hand, if the head of the water or the spillway is less than the design head, then the falling jet would adhere to the crest of the spillway, creating a positive hydrostatic pressure, thereby reducing the discharge coefficient of the. So, the several standard Ogi shapes were developed by US Army Corps of Engineers at their waterways experimental stations, and such shapes are known as the WES standard spillway shape. The downstream profile, so this is the downstream profile, which is represented by the equation x to the power of n equals k hd n minus 1 into y. So where x and y are the coordinates of the points on the crust profile with origin here at the highest point C. So now if this point C is the origin, so this distance is y, this distance is x. So this x and y are taken from the origin, and this downstream profile will follow this equation. HD is the design head, that is the difference between the maximum reservoir level and the crest. And K and N are the constants which depends upon the shape of the upstream face. So we have different profiles which is given here. So if the upstream face is vertical, so then the K value is 2, whereas N value is 1.85. If it is one horizontal to 3 verticals, then K value is 1.936 and N is 1.836. If the shape of the upstream face is 1 horizontal to 1.5 verticals, then K is 1.939, whereas N is 1.810. So similarly, to draw the upstream profile, the various parameters are given here. For example, so this is R1, this is R1, which is drawn like this, which is 0.5 times HD. From here, it is R2. And this profile is drawn like this, which is equal to 0.2 HD. The distance from here to this point is A, which is given by 0.175 HD, and similarly from the vertical face to the crest is B, which is 0.282 HD. So likewise for 1 horizontal to 3 verticals, so these are the parameters, and for 1 horizontal to 1.5 verticals, these are the parameters to draw the upstream profile. The discharge formula for the Ogi spillway is given by the formula Q is equal to C L E H E to the power of 3 by 2, where Q is the discharge, the flood discharge, LE is the effective length of the spillway crest, C is coefficient of discharge, which is taken equal to 2.2. HE is the total head over the crust including the velocity head. So velocity head is HA, which is VA square by 2G, where VA is the velocity of approach. Now we take the coefficient of discharge as 2.2, but it depends upon the various factors like the depth of the approach. So here the coefficient of discharge depends upon the ratio of height of the ogive to the design head. So height of the ogive may be 100, design head may be something like 4 to 5 meters. So given the problem. So now if you take the ratio of height of ogive to the design head, and if it is more than 1.33 times, then the velocity of approach is found to have a negligible effect and hence can be neglected. So therefore, the total head or energy head Hg can be taken equal to the design head. In such cases, C is equal to CD is equal to 2.2. But however, in the low spillways, when H by Hd is less than 1.33, then velocity of approach has to be taken into account. Then the curves are used to evaluate the value of the coefficient C, so which can be taken. So for example, for H by Hd, so if you calculate, okay, here that means total energy head divided by design head, then we get for the particular value, we'll get the value something like say 0.92. So then you have to multiply 0.92 to 2.2, and that you will get the coefficient of discharge. So you can modify the coefficient of discharge when particularly in the case of a low spill. However, there is no problem for high spillways where the height of the ogive to the design head is greater than 1.33. The coefficient of discharge also is affected by the slope of the upstream face of the ogive. If the upstream face is other than vertical, that is sloping, a correction factor is given, which is obtained from the curve. So corresponding slopes are there. So you can have. So if you take the ratio of height of spillway to the velocity head, this is velocity head, so then directly from the graphs you will get the correction factors, which can be multiplied to CD, that is 2.2, and then taken accordingly in the problem. And also there is an influence of the downstream apron as well as the submersion effects. So when the tailwater level, so this is the tailwater level which is given by D, okay. So when the tailwater is such that the top of the weir, so if this tailwater level is somewhere here, so that means it will submerge the ogive weir, and then it is called the submerged weir. So when the value of this HD, which is to the energy line, HD plus D, so this is total depth divided by the energy head, exceeds 1.7, then it has the negligible effect on the coefficient of discharge. The correction factor by which the value of C can be multiplied to get the modified value can be obtained from this curve. So now the degree of submergence should be known, that is HD by D value should be known, and then taken from this graph, okay, and multiplied to 2.2. So we'll discuss about the effects of actual prevailing head, because the head, the operating head can be less than or greater than equal to the design head. So therefore the spillway is always designed and constructed for a design head HD and the corresponding coefficient of discharge. But in actual operation, the same operating head will not be always equal to the design head. The actual operating head may be less or more than the design head. So since the design of the ogive spillway is done for the maximum head, the possibility of head exceeding the design head is very meager or very less chances. So when the actual operating head passing over the spillway is less than the design head, then the coefficient of discharge tends to reduce, which is given by this formula, which is C into H by Hg to the power of 0.12, where H is the total design head including the velocity head, and H is the operating head. For example, if the head is operating at 50% of the head, so then CD is say 2.2, so C is 2.2, which is a standard value for ogive spillways. And if it is operating at 0.5 times the head, total head, so then it will be the factor will be 0.92, and hence the coefficient to be taken is 2.02. However, for still lower heads, the coefficient of discharge goes on reducing and may tend to be constant at about 1.7. Now the effective length of the how to find the effective length of the Oki spillways. So we have the total length of this spillways, which will be divided into number of bays, okay, by means of piers. So there may be a number of piers. So for example, if there are four piers, so then there are 5 spans. So then the distance between pier to pier is the clear length. Suppose we have 5 spans of 10 meters, then the clear crest length will be 50 meters. Okay. So whenever the water approaches the spans, it contracts and forms what is known as the end contractions. So there will be end contraction due to the pier as well as end contraction due to the abutments. So the pier contraction coefficient or the abutment contraction coefficient depends upon the shape of the pier or shape of the abutments, and the values are suitably taken. So now the effective length of the Oki spillway is given by the expression, which is the total clear length minus number of piers. For each pier, okay, there will be 2 contractions, so therefore 2. Okay, this Kp is the coefficient, so Kp times n plus, because there are 2 abutments, so therefore 2 times Ka, so multiplied by He, where He is the total design head on the crust, including the velocity. So the values of Kp and Ka depends upon mainly on the shape of the piers and that of the abutments. For a square nosed piers, okay, square nosed is like this, without any rounding, so is taken as 0.1. Square nose with only the corners rounded like this, okay, then it is 0.02. Rounded is like this, fully rounded, okay, we have 0.01, and pointed is like this, pointed, so which is 0. Now the shape of the abutments, we have square, so like a square, okay, square abutment with head wall at 90 degrees direction of the floor, which K is taken as 0.2, and rounded abutment is like this, rounded abutments where K is taken as 0.1. So these were some basics of the Ogi spillways, where the formulas were discussed and that we are going to use in the problems. So now we'll take a very simple problem to start with, and we have to design a suitable sections for the overflow portions of the concrete gravity dams having downstream face sloping at 0.7 horizontal to 1 vertical. The design discharge is given as 8000 cubics. Height of the spillway is 204, whereas the bed level is 100. So 204 minus 100 is 104 meters is the height of the spillways. And spillway consists of 6 span. So if you have 6 span, then there will be 5 piers in between, and at each end there will be abutments. So each span has a clear width of 10 meters. So therefore 10 into 6 span will be the total, L will be 60 meters. Thickness of each pier is taken as 2.5 meters. Now for the trial 1, so since we know the discharge, so Q is equal to C LE HE to the power of 3 by 2, where LE is L minus 2 times KPN plus KA into HE. But since we don't know the head here, so we can't calculate this value. So hence the first trial we take as, that means we don't have any end contractions, so therefore assuming that there is no end contraction, so therefore LE will be equal to L, which is a clear waterway. So there are 6 span of 10 meters, so 60 meters. So taking approximately LE is equal to L, which is 60 meters, we can calculate the energy head. So energy head comes to about 15.5 meters. Now we know height of the spillway over the riverbed, which is 204 minus 100, which is 104. So we can calculate the ratio, which is 104 divided by this head 15.5, which comes to 6.71, which is very much greater than 1.33. Hence it is a high spillway. So velocity of approach can be easily neglected. So therefore HE can be taken equal to HD, and also CD value can be C or CD value can be taken as 2.2. Also the ratio HD plus D by HE to calculate the submergence effects, so which comes to about, the ratio comes to about 7.7, so which is greater than 1.7, hence it is not affected by the tailwater conditions. Now assuming that there is 90-degree cut water nose piers and rounded abutments, for this from the table we can take the contraction coefficient for the pier as 0.01 and the contraction coefficient for the abutment is taken as 0.1. We know that number of piers is number of spans is 6, so 6 minus 1 is 5. So hence we can calculate the effective length. So knowing L, knowing Kp value, N value, Ka value, and hence from the previous step we know we have calculated He, which is 15.5, and hence the effective length comes to about 55.35. Hence we can go back to the again we can have the calculations, which is Q is equal to C LE He to the power of 3 by 2, where Q is known as 8000, C is 2.2, LE is calculated, and hence again we can calculate the value of He, which is 16.3. In the previous we got 15.5, now we got 16.3. So if we can go on doing the trials till these two values are same. So hence coming to trial 3, again calculating the effective length using the new value of He, which is 16.3. So again this value comes to about 55.11. Hence Q is equal to C LE He to the power of 3 by 2, which is 16.33, which is very nearer to 16.3. Hence we stop the calculations. So however, though velocity of approach is neglected, we can still calculate the velocity of approach, because discharge divided by area. So total length is 60 plus 5 times, because the width of the weir, so total length we get, so 2.5 into 5 plus 60. Total height is 104 plus the depth of the water is 16.33, so that gives the area. So hence the velocity of approach is 0.917. If you calculate the head due to the velocity of approach, comes to just 0.043, which is very small and hence can be neglected. Now the downstream profile, which is the WS downstream profile for the vertical phase where vertical upstream phase is given by this formula, where okay, so x to the power of 1.85 equal to HD 0.85y. So we can get the value of y by substituting the value of HD as 16.33, which is y is equal to x to the power of 1.85 divided by 21.48. The downstream slope is 0.7, so therefore dy by dx can be written as 1 by 0.7. So now you can differentiate this expression, so therefore it is 1.85 differentiation of x. Okay, so 1.85 x, 1.85 minus 1 is 0.85, so divided by this, it should be equal to, so you can calculate the value of x, which comes to 27.23. Substitute this value of x here and we can get the value of y, which is 21.03. We can work out the ordinates by using the expression, okay, by taking various values of y. So at least 10 values should be there. So we have calculated each of values like values of x for a corresponding values of y. So we know this in this figure. So if this is the crust, so from crust this is y and corresponding x. So for example, if y is 7, so for example 7 and corresponding x value is plotted. Like this, various points are plotted which follows this equation. And we also have discussed for the upstream phase vertical, we know what are the values of R1, R2, A and B, so which can be suitably calculated and plotted. So these are the values of R1, R2, A and B, which is calculated and hence plotted. So this is the upstream profile, this will be the downstream profile, which is asked in this problem. We'll take up the next problem, which is Again, similar to the first problem, where we have to design a suitable section for the overflow portion of the concrete gravity dam, having downstream face sloping at 0.8 horizontal to 1 vertical for a design head of 2 meters. In the previous problem, the design head was not given. So in this problem, a design head is given. In the previous problem, the discharge was given. Here, they are told to compute the discharge if the coefficient of discharge is 2.2. So height of the spillway is just 8 meters. Spillway length consists of 4 piers of 1 meter width having rounded ends with each span equal to 10 meters, and abutments are having square ends. Now we know that for rounded nose piers, okay, Kp is 0.01, and for square abutments, K is 0.2. It is also given that the coefficient of discharge is 2.2 and the design head is 2 meters. We have number of piers as 4, so you can calculate what will be the spans. So number of spans will be 4 plus 1, which is 5. So now the clear crust length, because each span is 10 meters, so 5 into 10, which is 50. Now the first trial, so we can assume HE will be equal to HD. Okay, in the previous problem we assumed LE is equal to L. Now we can, because the design head is given, so we can equate to HE and hence calculate the effective length, because we know the clear crust length, we know Kp, we know N, we know Ka, and hence we know 2 meters, which is HE. So hence the effective length is calculated. Using this effective length here and 2 meters for HE, we can calculate the discharge, which comes to about 305.15 meter cube per second. Now given that the height of the spillway over the river bed is 8 meters, so we can find the ratios, that is 8 by 2 is 4, which is greater than 1.33, hence it is a high spillway. So velocity of approach can be neglected, hence the reason that HE will be equal to HD is taken. In such cases, C is equal to CD, which is 2.2. However, the submersion effects also can be calculated by this formula, and hence the ratio comes to about 5, which is greater than 1.7. Hence discharge coefficient is not affected by the tailwater condition. Though the velocity of approach is very minimal and also the velocity head is very less, still we have calculated the velocity of approach by discharge divided by the area. So the clear is 50 plus there are 4 piers of 1 meter, so therefore the total length into the depth. So 8 is the height of the spillway and 2 meters is the height of the water, so therefore we get the area, so that gives 0.565, so which is 0.0, because the velocity head is 0.016, which is very less. Still we can calculate. It is no harm that we take even H is equal to 2 meters, but still since we already calculated, we can add HA, that is 0.016 to this and get us 2.016 meters. Now using this value, we can calculate the effective length, which comes to 49.03, and again calculate Q value, which is 308.76. So the previous trial we got discharge as 305.15, or in this trial we get 308.76. So we can do one more, like find out the new velocity of approach, which is 308.76 for this for the discharge, and the area, so we get 0.572, and hence the velocity head, which is last time it was 0.016, now it is 0.017. So therefore the design head is 2.01, which is design, and the total head is design head plus the velocity head, which comes to 2.017. This effective length can be again calculated as 49 using the new value of HE, which is 49.03, and hence the discharge can be calculated. So last previous trial was 308.76, whereas here we are getting 308.99. Since these two values are almost close, we can stop the. Similarly, the WS downstream profile is given by x to the power of 1.85 is equal to 2 times HD to the power of 0.85 into y. So we get an expression for y by substituting the value of HD, which is 2 meters. So hence we get x to the power of 1.85 divided by 3.61. So differentiating this equation, so we get this, so which is 1.85 x 0.85 by 3.61 should be equal to, because the slope is given as 0.8 horizontal to 1 vertical, is 1 is to 0.8, so x value can be calculated. So x is 2.8. Substitute the value of x here and we get the y, which is 1.93. Now are worked out. for various values of y we get the x. So that is been plotted here. So for various values of y we get x. So this is the downstream profile which corresponds to this equation, and we have the upstream profile which the various values of r1, r2, a, b are given or calculated. So which is given here. So for HD, which is 2 meters, we calculate R1, R2, A, B, which is been plotted here, and we get the upstream profile, and this is the downstream profile. So coming to the last problem, we have the which is again similar problem, where we have to design a suitable section for the overflow portion of a concrete gravity dam having downstream face sloping at 0.7 horizontal, 1 vertical. Here again the design discharge is given, which is similar to the first problem, where it is 8500 cumex or meter cube per second. Here I to the spillway is again 100 meters, but the permissible level of submergence, that means the design the design head above the crust should not should be less than 10 meters. Okay, so this is the permissible level, which is 10 meters. So HD is 10 meters. It can't exceed more than 10 meters. And also it is given that the permissible span should not exceed 12.5 meters. So these are some of the two restrictions which are given in this problem, which is quite different from the previous two problems. And thickness of each pier will be taken as 3 meters. You have to find the length of the spillway. Piers and abutments are the rounded type. We have to take C as 2.2. Now in this case, to start with, so to calculate, because the discharge is given, so we can calculate effective length if you know the head. So that's the reason why we have assumed first HE is equal to HD, as to start with 10 meters and calculate the rough value of the length, effective length. So height of the spillway is 100 meters. So the ratio can be calculated with H by HD as 10, which is greater than 1.33. Hence it is a high spillway. So velocity of approach has a negligible effect upon discharge. So as such, we can take HE is equal to HD. So C value can be taken equal to 2.2. However, the submersion effects can also be calculated, where the ratio comes to about 11. So which is greater than 1.7. Hence the discharge coefficient is not affected by the tailwater condition. Now we have for the rounded nose piers and rounded abutments, the Kp value is 0.01 and Ka value is 0.1. So since we had the effective length as 122, so roughly we have assumed 12 spans. So therefore the number of piers are 11. So okay, maybe around the span is around 10 meters, say. So now we calculate what the knowing effective length in the previous trial 122.2, we can calculate what is the crust length. So the clear crust length, taking H is equal to 10, so that comes to about 126.4. So say we can say purposely increased to 132, so that we get a clear 11 meters 11 meters clear length, which will be less than the clear length of 12 points. So because the maximum clear length should be 12.5 meters, here we have, because the number of spans is 12, we have taken as 132. So 132 divided by 12 comes to about 11 meters, so which is less than 12.5. So we have to see that, so when you take this the 132 meter span here and calculate the effective length, okay, calculate, because H is here 10, so therefore we get 127.8. okay, so using this 127 we can calculate what is the head. So head is 9.7, which is less than 10 meters, and that's the adjustment that we have done. So now for the next trials, so since we have taken as 9.7 as the design head, so this trial is number of trials are done till these two values are same. So now we have fixed the span, which is 11 meters, which is less than 12.5. We also have fixed the total energy head, which is less than 10 meters. It can't exceed 10 meters. Trial 3 is that we knowing the new value of 9.7, that is the total energy head, so 9.7. so now L is 132, so which you have fixed to because there are 11 meters of 12 spans, so there are 11 piers, so therefore we can calculate effective length. So using this effective length, we can again calculate the total energy, which is 9.7, which is same as the previous trial. However, we can calculate velocity of approach by the total discharge divided by the area. So each pier is 3 meters width, so 11 piers. Total clear is 132. So total length we get, total depth we get here. So therefore 0.47, and the velocity head is very negligible, which is 0.011 meters, hence can be neglected. In the similar fashion, we can calculate the downstream profile as per WS profiles, which is given by x to the power of 1.85, so 2 times HD to the power of 0.85y. So y can be calculated in terms of x, okay, by substituting the value of HD as 9.7. So we get 13.8, x to the power of 1.85 divided by 13.8. However, the downstream slope is 0.7 horizontal to 1 vertical, so differentiate this. So therefore differentiating, we get 1.85 x to the power of 0.85 divided by 13.8 should be equal to 1 by 0.7. So we get the value of x, which is 16.2 meters, and corresponding value of y. Substituting 16.2 here, we get y. Various values of x can be calculated by substituting the values of y from y is equal to 1 to 12.52. So therefore this is the origin. So for various values of y we get x. So the downstream profile is plotted as per this ordinates calculated using this equation. And also the upstream profile can be plotted by knowing the value of A, B, R1, R2. So from the crest we have to mark R1. So this is R1, taking this as center. So now draw an arc till it cuts the A line, so therefore we get here. So from here mark R2. So this is R2, mark B line. So from here draw an arc from here so that it cuts B line, so this line. So we get an upstream profile. So this is the downstream profile. This is what's shown here. So we know how to calculate R1, R2, A and B by various formulas which is given. So R1 is 0.5 times HD, R2 is 0.2 times HD, A is 0.175 HD, B is 0.282 HD, where the design head is 9.7. So various values are calculated and accordingly plotted. So we have discussed the spillways, particularly the Wogi spillways. So how to take the discharge formula, which is given by C LEHE to the power of 3 by 2. So we also discussed how to take the coefficient of discharge, what are the various factors that affect the coefficient of discharge. So when we have to consider high spillways or when we have to consider the low spillways, and what are the corresponding values of coefficient of discharge. And also we have discussed about the how to calculate the effective length, because the effective length will be not equal to the total length of the spillway. Definitely when the water approaches the spillway, there will be contractions at the piers as well as at the apartments. So the various it depends, these coefficients Ka and Kp depends upon the shape of the piers and shape of the apartments. It can be square apartments, can be rounded apartments. Here it can be square piers, or it can be rounded piers, and accordingly the coefficients are taken. So using the various, and we also discussed about the various WS standard profiles, where the equations were given by WS standard profile equations, which were developed at the waterways experimental stations, and we have used in the problems. And we have discussed three problems where number of trials have to be done and how these trials are done till the particular values will remain same in different trials. And then we go ahead with knowing the discharge and the effective length and the head, design head. We can go ahead with the downstream profile calculations as well as the upstream profile. calculations. So thank you very much, and hope you had a very good session on spillways. I hope you will revise all the lectures that I have done, and if any doubts are there, you can always contact me. And hope to see you in the next series of lectures on spillways, where I'll be covering the types of spillways, and maybe so that various types of spillways in this, and also more importantly I'll be covering the energy dissipating devices which are provided just below the spillway. Thank you, thank you, thank you very much.